Close the door. Do it like this. Okay, perfect. Okay, so welcome everyone. I mean, sorry, to the seminar. Okay, now I have to play both roles. So, as an invited speaker, let me thank the organizers for giving me the opportunity to speak here and present our work, which is done in collaboration with Julian Kupka and Charlie Strickland Constable. It's about the BB formulation of 10 dn equal 1 supergravity. So I've given talks of similar nature before, and I noticed that there is always this issue that there is some slight technical details that need to be introduced, and then usually there is not much time afterwards to delve into some other interesting aspects of the story. So I decided to present a little bit differently today. So I started by writing the results. So this is the BB formulation of n equal 1d equal 10 supergravity. This is for people who know generalized geometry and or supergravity. Also, I introduced two typos in there because I suppose there will be people that. But anyway, does anyone see any two typos in there?
63.
60, thank you.
It's about 60.
Very good. That's first typo.
So the thing is that the movie the camera following you.
Oh, yes, you need to go to the hello. Go to this thing. Yes, and then click on this one. Sometimes it does it so. No, to the tab unlock. I don't know, it doesn't matter. This one. Now it's locked, and now let me go to the. Apologies for this technical. This is the modern technology. But yeah, I shouldn't raise my palm because I start.
But 63 was aesthetically kind of more appealing, like this little bit lack of symmetry, like in people's face, which makes it beautiful. I think that it's perfect.
Right, but there is still one typo in there. You can try to find.
Oh, so
there was two. So this was one. So good job with putting this one.
Okay.
There is another one. That's more of a syntactic typo. But okay, while the audience is busy looking that way, let me say so. So this is again, this is for people who understand general geometry and of course supergravity. I want to kind of the goal of the talk is to kind of explain the structure behind and like where does it actually come from and what it actually is. But I will focus more on like the PV aspects of the story in generality. So this will be like a particular application. But I want to talk about some other geometric aspects which I find kind of interesting and which kind of are independent of this one. But anyway, it's all going to be about that secretly, but not really. You don't need to really know the details. But let me still spend a few words on saying, defining a couple of objects for people who have seen this thing before, and then I will proceed from the beginning about what is BB, RST, and all that. Okay, so what are we looking at? So this is the 10 dn equal 1 supergravity. So this is the theory that's like the two derivative part of the low energy effective action for superstring theories of heterotag and type 1 superstring theory in 10 dimensions. And that's the theory. So it's a theory which describes some fields. So metric, a B field, a connection, and all that. And then
Maybe I found the typo. So here on the right, there's like two lower indices A, which probably one of them should be lower, one of them should be upper.
Where?
On the right, it's like very right.
Here?
Yeah.
Oh yeah, okay, then that was a third typo. Thank you. Thank you. That's a good one. Okay, I count that as another. So there is another one.
made on purpose, right?
Sorry?
Made on purpose.
Yeah.
To
To
test it.
exactly. So okay, okay. So yeah, there is a theory in the dimension. It's kind of relevant for string theory, also relevant for some mathematical considerations. We have it in the end. And it has a complicated symmetry structure and all that. And the thing you see here, so actually the theory itself, classically speaking, would be these first 3 lines. The rest is kind of the BV description. I will explain what that means. And second, let me just say again for the experts that like the setup here is an arbitrary current algebroid, unrestricted dimensions or anything. The only thing you require is that when you put the generalized metric on it, which is the same as an orthogonal splitting of this thing, then you want that this guy has a signature 9-1. That's kind of the only, and he has spinners, so things like that. This is like there is a spin left. That's it, and then you can define all these objects. So the green, which is not really even I don't see that it's green, but this kind of green. No, sorry, not the green one. I missed the colors. Okay, the pink one is the kind of objects, how they are called in generalized geometry. The green one, is not really green, is how they decompose in terms of ordinary objects in ordinary geometry. So this parallel G, which is generalized metric, decomposes into metric, a B field, and then in a connection on a principal bundle. That would be one example, and blah blah blah. And right. And this decomposition into these green ordinary geometric variables, for that you need to have this. I was supposed to write this in green, but I confused the colors. So so this reduction of these ordinary geometric variables happens if the current algebra is transitive and if the anchor satisfies some of the isomorphism condition. But for the theory to make sense, this is enough. Okay, this was for the experts. Still waiting for the title to be discovered.
I think I'm gonna. There's an alpha. There should be a beta, right?
Exactly. Very good. Very good. It's a good audience. Thank you. Okay, so this is that. I will keep it throughout the talk as we will glimpse more and more into the. I mean, as we will understand more and more structure of that. But let me now say that. Oh yeah, maybe some self-advertisement. I should say that this is the first time, as far as I'm aware, that the BB formulation of a higher dimensional supergravity has been achieved in a background independent way. So there is, so in a sense, if you know about BB, then BB was kind of discovered or like introduced in order to study systems with complicated symmetry, such as for like most prominent supergravity theories. But up to now, I don't think there was a good formulation of higher dimensional supergravity that would work in any background. So this one does work. You're looking at it. Pretty cool. Okay, so now let's take a few steps back and let me start with some more basic stuff. And let me tell you what BRFC is for those of you who know, and for even for those of you who know, I don't know. So, okay, so what is the start? What's the idea? So the start is that you have a manifold. Okay, this is my explanation of what is happening with an action of a Lie group. And there is a function, a smooth function on M, which is G invariant. And now, if you're a physicist, then the problem that you're interested in, very roughly speaking, is that you want to calculate some integrals of this form, so-called path integrals. So what you should have in mind, if you wish, is that this is your space of all fields, so some horribly infinite-dimensional space. This is some very, very large group, so some infinite-dimensional group. And this thing is a function, the action function. And so here I'm just making a finite-dimensional polynomial of that. Okay, so as a physicist, you want to calculate expressions of this potential with some more integrals. And this is schematic. Okay. But the problem is that you want to do it perturbatively, but it's hard. And if you want to do it perturbatively, then the standard approach that you are doing is that you need to take critical points of this and you need to expand around it, and that critical point better be non-degenerate. But here it is degenerate generically because this action is G invariant, so the critical points will form G orbits, which are typical, not just points. The problem is that this is degenerate. It has degenerate critical points. Hence, you cannot just use the usual lore, which is just like take a critical point, expand around it, look at the quadratic part, invert it. That's the propagator, and then you just stop with it. So you cannot do that. So how do you solve this? Well, there are several ways. One way to solve it, if everything is going well, is that you simply take a quotient. Quotient it out. This thing will then hopefully will become non-degenerate. But quotients are often well behaved, as you know. So what do? You resolve. So the idea is that if you take a new manifold, I will call it currently M, and you take this to be the product, the manifold with the Lie algebra of the group, which you shift to be degree 1. And coordinates on this you shift to be of degree 1. Not me, maybe it's called coordinates xi, and this one ca. And okay, you have a new space. It has now some gradient, so we also introduce some differential. This is a vector field on that space. It has that form. Okay, so this thing here, these are the fundamental vector fields. So the generators of this action, and these are the structure for each of the algebra. And this thing has a nice property that it's square root of 0. It is of degree 1. It gives a complex. First is a complex on the algebra of functions here. And the idea is that you can replace this thing by some sort of cohomological problem. So now you can show that the cohomology of this recovers G-invariant functionals on M in particular. And so everything is kind of moved to this cohomological mode. But then how does it solve your problem? So the way you solve it is that because it's now cohomological, okay, here I'm just tossing words around. So you like to regard everything that's exact as being kind of the same as 0. So you can add some stuff. You are actually. Yes. Yeah. Okay. Written in. Yeah. It is, in other words, this is what is called an action Lie algebra of the for the action of this group or algebra on. Right. So then what you do is that you take this Q and you add something Q exactly here, and morally you are supposed to, even if you can make it formal, like this actually doesn't really change the logic of like the stuff. But now by adding something to this, you might achieve now a non-degenerate of the critical point. So here, hopefully, now non-degenerate the critical point.
Does it always work, or there are some conditions?
For Lie algebra actions,
Well, it's enough for me.
is it?
I guess so.
Okay, probably.
So it works.
Well, I don't want to make any strong claims about it, but that's how I hopefully. Probably.
I think so.
Okay.
Because I mean, it looks like a standard deformation.
Yeah,
So
yeah.
it's actually like going from, let's say, more spot situation to the more situation when you have, I don't know, you don't have like a discrete type of like a critical points, or you have many critical points and you try to deform. So it's the same thing.
I see. Okay, thanks. Yeah, so right.
And here you assume that G is finite dimensional.
Oh yeah. Everything is finite dimensional, but then I would just pretend everything is still finite dimensional, even though it's blatantly it would be a lie. But yes, here it is. That's kind of the logic of working with in quantum field, that to pretend everything is compact and finite dimensional. Kind of. Maybe not always. Okay, so this is how you kind of solve your problem. So you enlarge your space. Now you're playing your game in some larger thing. But now there comes another step that you can do as VB. It's not really necessary in this way I'm saying, but still it gives you some new light. So VB stands for bottom of obviously. And this is Beck-Hero storage thing. So what we do here? So forget about the details. Just remember that you have a gradient manifold. You have some vector field with square root of 0 on it, and you have an action, which is a function of ordinary n, but you just pull it back to this.
Yeah, because we have some kind of problem with the video, and
Really?
there is no video.
I see.
But this problem just appeared recently, so it becomes. Here the image is shown kind of inverted, but
That should be.
it's okay.
Well, normally yes. What if you change to the virtual camera?
So
Okay, that doesn't that breaks it. There's a technical break. You can look at the formula and set for more typos.
Because everything's working okay, but they're somehow getting no image.
That's very strange.
Maybe the camera is also looking for a type.
Sorry?
Maybe the camera is also.
Maybe. Should we just unplug the camera and plug it again?
But it's part.
Because what we can do here.
Yeah.
Okay, so now we just pick it.
So what about now? Does anyone see anything? Any progress? Wait,
Yes, I can see.
Okay. Okay. Is also the sound? Should I repeat everything that was said?
No, the sound kept coming through all the time, but the board was
Okay, I
closed
was
for a
writing
few
everything.
minutes, maybe like 4.
Okay, can you also see this in real motion like this? Really? It's small. Okay, I will write bigger. Okay, thank you. Okay, but you can see the movement, right?
Yes. Yeah.
Okay, good.
What do you write to the what do you write to new to the left? I think that for me is readable.
Okay, thank you. Okay, good. So, okay, what are the obviously? So the moral so far was that we now have a space, we have a vector field which squares to 0, and there is a function. There's a function here, but really we can just pull it and roll back. So there's also a function in here. Now the idea of DV, one way to look at it, is that you replace this thing by a larger space. You take the shifted cotangent bundle of that thing. Okay, so now for every coordinate here, you enter in a cotangent coordinate, which will be of degree shifted by -1, as opposed to the normal gradient. And okay, what do you do with the rest? You add it together. So you define a new function on this cotangent bundle, and you take it to be the sum of these two. And now why can you do that? So because this thing was a function, and this thing was a vector field on M. But functions of M, that this thing was a function on M, but functions on M you can pull back by the projection to the cotangent bundle, right? So that's fine. You have a maximum cotangent bundle to the base, you just pull it back. That's the meaning of this. Now vector fields, so FQ was a vector field on the base, but vector fields on the base are particular class of functions on the cotangent bundle. That's the meaning of the cotangent bundle. One interpretation of the cotangent bundle is that you have a vector field, and that gives you a linear function on this guy. You just replace partials by p's. That's the meaning of this one. And if you add it together, you can check that it's kind of the degree is all right, and in fact, you can show that the non-trivial statements from before, namely that Q squared to 0 and S was Q invariant, which was kind of the G invariance of the thing. They correspond to this equation for the plus in bracket of the cotangent bundle, which is called the classical master equation. Okay, so that's one way to look at it. Now, why is this better? Well, okay, for one thing, we now have just two objects. We have a symplectic manifold. Okay, that's really two objects. You could read that before, but anyway, but there is like 2 slots in this part of this instead of 3. See, that's already improvement. So you have a function which satisfies classical master equation on a symplectic manifold. So now, okay, well, again, why is this good? So there is, apart from having just sort of less degrees of freedom, maybe, one way to get the advantage is that it gives you some geometric interpretation of what's going on here. So this is the picture of the shifted tangent bundle, and inside it you have the manifold M sitting as the 0 section, and this thing is Lagrangian in this manifold. And the kind of the punchline, or one of the punchlines, is that modifying your action by a Q-exact piece here corresponds, in some sense, to deforming your Lagrangian to some nearby Lagrangian. There is some other Lagrangian. It has to be a particular type of deformation. I think it has to be Hamiltonian deformation, very correctly. But anyway, the idea is that you. I mean, it's pretty simple. So it's just this trick of adding stuff here corresponds in here in some way to just deforming this thing, because in the PV framework, what you are doing is actually you are calculating an integral over Lagrange and some manifold instead of this, and now changing the integration locus corresponds with adding this Q in here, and you can achieve some non-degeneracy some suitable. So okay, so the punchline was that it just gives some nice geometry. But also for us, more importantly, the second point is that now you can do more general stuff. And do more general stuff. Just note that. Oh, I didn't write it. Okay. Yeah, maybe for those who like more precise formulas, so this SBV, if you want to write it in terms of coordinates, and what it gives you is just you take literally that formula, and you just replace partial derivatives by the momentum. The momentum I will just call same as the coordinates, but with a star. So, and minus 1/2 F A B C C B C C C star A. Sorry for those who are watching. I just took that and replaced partials by P's. But where P's are the star variables. These are potential variables. So here we have X and C, and here we have the cotangent coordinates X star and C star. Now, one thing you can see in is that plus S. Okay, S plus Q. Now, one thing you can see here is that this expression is at most linear in the cotangent direction, in the cotangent coordinates. So what BV allows you to do is that you can go beyond that case, and you just postulate that you want to have some symplectic, graded symplectic manifold, and you want to have some function which satisfies the classical master equation. And there has to be some degrees, like this has to be degree -1, this has to be degree 0, whatever. But you can do more general stuff. In principle, you can have functions which would be of the cotangent bundle, but which would have more higher polynomials in these star variables, which are incidentally called anti-fields. Okay, so here you can do more general stuff, and what I mean by more general stuff, right here, i.e., we can have cases where we have some space of fields and we have some action functional, and distinct invariants not under a group action, so we can have some very much more complicated stuff, but it's invariant under a bunch of vector fields. On which don't have a nice form. For instance, that if you commute them, then you get another of the class. Like it's not like a representation of some Lie algebra or even a Lie algebra. It's something like you can just imagine that they have a bunch of fields which are pretty random looking, and they don't satisfy any nice algebra. And this is kind of the framework you want for that, at least in some special cases.
Usually, you get like something that has structure constants depending on n, and which closes through a closed equation.
Yes. Okay. So
This is the case when
right. So yes. So right. So when there are much vector fields, whose algebra only closes on shell. So there is a class of vector fields, and if you commute them, then you don't get a member of that class, but you get a member of that class on the critical locus of this action function. That's what it means on shell. So something very complicated. That's what happens for supergravity. So okay, that's the very one. Any questions? Oh, okay. Okay, then let me continue with. Now let me say a few words. Let me say a few more concrete words for those who like general geometry and want to see actually that theory. And then I will discuss some general considerations for a few theories in general. But okay, so what is the theory? What is the theory question? So the set data is that you have a principal G bundle. For G, okay, so this is something So the Lie algebra that we want it to be quadratic, so we want it invariant pairing. That's the data. Now, on this, you can now define field theory where the field's content will be given by the metric. Lorentz metric of signature man, I, this is standard dimensional. And dimensional manifold with the principal G bundle, otherwise arbitrary. Probably want this to be compact for probably want this to be E8 times E8 for SO32. That's okay. So the field content is given by this guy, then there is Lorentz metric, there is two form B, and there's a connection, so the G connection. And there is a function, usually phi, just the dilaton. And then there is a bunch of permanent variables. What we call them gravitino, Kgino, and dilatino. They are called like that because they are partners in some sense of these guys. The gauge field, gravity. So they are not really actually, but that's where the name comes from. Okay, so now what does the general geometry do here for you? General geometry or Courant algebras. Again,
defined or from
which one B or
yeah.
no, I don't think it to be globally defined. No, okay, yeah. I mean, it's a little bit more even general than what I wrote, but yeah. So this is kind of like a connection on the curve. So it's really it's two form in the same sense as this thing is a one form, and then this is not a one form, and so this is not a two form.
No.
But locally, that's fine. Yeah.
Okay, so then the H should be integral. If you say it's maximum, assume that it's integral.
Well, if it's U on Earth, then I guess yes.
Yeah, if you want, but you don't.
No, for this I don't really need that. For this is kind of classical. I mean, although I mentioned some pragmatic class, this thing I'm doing is not classical, and I really don't need that. Properly, we will take some sort of integral. Okay, so now what happens in general geometry, or otherwise known as theory of Courant algebras, let's say, is that you replace this setup by saying that you have a Courant algebra. Again, no need to know precisely what it is, but if you do that, it's very good. This is just a vector bundle in the product plus extra structure, bracket. That's what replaces your setup here. And now on this, you can play your game and you can introduce the fields that are entering there. We'll have some first field metric, which is really a map, vector bundle map from E to E, which is symmetric and squares to the identity, which is in a sense the same as splitting your E into its eigenbundles. So these are this thing gives you an orthogonal decomposition of your vector bundle into two subbundles. And the condition I require is that this thing actually has signature 9-1. And the only thing that I really need there is and is spin. So admit spinner. Everything else is optional, but this condition is important. And okay, so now we dealt with spinners, then we can so call S C plus, it's substitute plus minus the Majorana Mayer spinner bundles. Okay, so this is just something that comes from the representation theory of the orthogonal group. Yeah. So this just means that if this is a bundle with the signature 9-1, you can construct a Clifford algebra. You can study the spinner representation of that. of the, okay, sorry. You construct this, you consider the corresponding spinor bundle, you construct representation, and there is particular two distinct ones which are real. And yeah, full stop, and they are called Majorana bundle. And there's two of them. So there's bundle for n. And now having that bundle, now you can define other fields that we need. So first of all, there is, we should have said, so this generalized metric, and then there is a dilaton, which for us is a section of H, where H is this is the line bundle of Hall densities. And so this is just, if you don't know what Hall densities are, you think of this, like a half of a density. So if you multiply two such things, you get density which you can integrate. Squares of these things are naturally integrated over m, even if m is not oriented. It's not m. Just think of it as a function if you want.
So the C plus and C minus have to the same dimension.
No, not here. No. Yeah, it's
C plus is 10 dimensional.
C plus 10 dimensional. But yeah, you can even consider an interesting case where this thing is actually zero. So you take this to be the entity. That is surprisingly still quite interesting. Okay, sorry, you want this to be invertible. I should have said that. Okay, everywhere non zero. So then you go start. This is the bosonic fields. This is up there. But now we have spinors, so we can define the two fermions. So let me say what they are. So gravitina is a section of, okay, here you can choose, I think we choose minus. And it has the vector index, C minus, and it's a half density. And this one is positive chirality, and it's a half density. Okay, so this might not look like much, but it's actually very important. It's kind of very, very crucial that this thing is a tensor product. It's a section of tensor product where this guy uses C minus and this guy uses C plus. So it has kind of a spinor index and a vector index, and they are not interacting. They are restricted to different bundles. That's important.
So then C minus is 0.
Then this is 0. Yeah. And this one is actually frozen because you cannot vary it by preserving this condition. So then you get a theory, which I want to get to the end, but now I can say, if you do that, then that gives you a meaningful theory, which where the only field that you have is like inverted for half density, this kind of guy, and that's called the dilatonic supergravity. Because you have dilaton and dilatino. And it's a locally supersymmetric theory. It is topological, and it's kind of cool. Although a little bit pathological. So, right. So now, okay, without further details, this is what generalized geometry business is about. So, having specified such data, you can now construct several interesting operators. This is a talk for today, or it's not too difficult, but here we just need the result. So we can construct some operators such as this, such as the Dirac operator, and they are all defined, and they act on. They kind of want to act on these spinor bundles or spinor tensor vectors. This one, but they twisted by how densities. And etc. So there's a couple of operators that you can do, and those are the ones that you see in here. Everything you see a B here, and that's an operator constructed using this data. That's the explanation for that bit. And now, let me pretend that I'm now more mathematical. Let me say theorem. So this is our paper last year. Which says that there is an action, functional, which is precisely these first 3 lines. So now I get to the point where I can actually explain what's happening. Okay, so it's a good thing. Let's call it S. That's a bit which doesn't have any anti-fields, doesn't have any of these start variables. So that's action. It depends on T, sigma, Psi and rho is invariant. There local supersymmetry on the form. Now I have to say how these things transform. So if I pick a parameter, which is now a section of okay, I should have specified that these are odd, so let me put a capital pi here. So these are odd sections, odds. These are shifted parity. Same here. So there is a spinner of negative gravity here on density that is specified. I want to specify such a section that you can describe the transformation metric, which is here 1 sigma minus 2. That this bit which is of A and B. So I mentioned it, no, actually I maybe didn't mention it, but I use Latin and Greek for C plus and C minus indices. It's not really important. So feel free to forget this information. Just explain why there is Greek and Latin. And for instance, the Villapinto transforms this. There is some relatively complicated formulas. Which might last about a year to do this.
So G alpha beta is defined on the section space, on the bilinear form of the space of sections. Baby G alpha beta.
So G is a endomorphism of E. So it really goes from this guy to itself. But if you vary it, so if you take these two conditions with actually the first one. Okay. So I should say that the tangent space to the space of such structures is the same as the tensor product of C plus and C minus. Plus minus. So that's why I only go to plus minus.
Actually, you have it on the sections.
Yes.
Or you can.
But it's point. Yeah, it's point. Yeah, there's lots of there are some of them quite interesting, but yeah, you're perfectly right. That's why there's the other parts are zero. Okay, so here is some gamma matrices, which is just the way you encode the algebra of the SL91 group. And you have the similar formulas for the other two terms. So these are relatively complicated formulas. So proof of this is, I dare say, hard. But it's much easier than corresponding statements. So this is the proof that this is really a superconducting theory. The thing that they constructed. And I wrote down. And moreover, if you look at these formulas, then and if you look at the story of how this BRST and this framework works, then if everything was going well and there was really a group action, then you see that the action that you are expecting should look like classical action, and there should be some terms proportional to these starred variables. So, and those terms, proportional to starred variables, they encode the fundamental vector, the action of the group, which is this guy. So this is the explanation of the next three lines. So the next three lines are nothing else but the description of this thing. For instance, it tells you that the G transforms under supersymmetry, which is E guy. The G transforms under E by this formula. This is how you get this one, and the same for rho. So these next three lines, this is nothing else, but this tells you what this is a compact way of saying what the actual symmetries are. And there is the kind of easy thing, which is the Lie derivative, which I'm kind of, because it's kind of easy, I'm skipping over. But there is apart from supersymmetry, this thing has another large symmetry, which is the symmetry under ecomorphisms, or more precisely generalized ecomorphisms.
I think the people I'm confused totally. Supersymmetry. You mean really acting by infinitesimal supercon correct? Or the analytical probably variational shift written by this delta epsilon.
Right. So this thing is a local supersymmetry, which means that it's not just
This thing It's two rows.
Yeah, but they are parameterized by this epsilon. Epsilon is like
This is the supersymmetry.
yeah. So this is
It's the action of the superform current.
it's not actually it's a local extension of it. So it's like which means that it's like you have, instead of having choosing a parameter in superconcatenate order, you choose a section of a bundle.
But I can imagine that just for fibers, you can say it is supersymmetric invariant if it is invariant with respect to the action of G, which may then form, it's which is different from this analytical variational approach. Let's say that I don't see it there.
Yes. So the transition. So that's okay. So there is a sort of big difference between the supersymmetry and local supersymmetry. So the thing you're saying is the supersymmetry. Yeah, no, but like the local here is kind of is a big step. So supersymmetry would just mean we have a super Poincare group, and that would really be this group acting. Now this thing is much more complicated. It's not even a group. I mean, these transformations, they do not form a group. They don't also even form even infinitesimally. They don't even form.
Not a problem yet. Okay, we can discuss it.
No, but it's a good point. But there is a okay. Let's talk later. Right. So these three lines, they just tell you what the transformations of fields are. And then, as expected, and then if you look at the last term here, then the last term, which is proportional to the antifields to this C guy, that should be the next couple of lines. 2, 1, 1, 2, whatever. These guys. And they should correspond to the algebra, so they correspond to the structure coefficients. That's okay. When do we usually go on to the more, or do we start from before? How the seminar?
How long?
Yes.
You can go for like 14 more minutes if you have something to say.
14
or 14
Okay.
right?
Good. Yeah. That. Also, I have one. I could have just clicked on it. Okay, so then let me address two.
Maybe a really naive question.
Mhm.
So basically in the setup, right? So you already said that you have only locality for B things, so say that it's 2 from 1. So in your statement, right, so it's in the result of the theorem, you also have locality. The understand correctly is that even if your B and A are globally connected, so even if you mention this type of scenario, the theorem still the locality. So
It still holds. Yes.
it's still local. It's still local. It's not global.
No. I mean, no. This is a global. The thing I wrote is
If it is this is local.
no. This is global. It works globally.
I see.
So there might be things that look like indices in here, which might look like you are taking some like local frames or something, but in fact they are not. They are just like a way to say that you have your contracting bundles and like something. So these are global expressions. So it is. I mean, actually, even this one, it looks like there's indices here and there, but it's actually completely index-free in the sense that they just tell you like that you have to have a tensor product with some bundles, and you are making the contraction of them. So all this is local, and each term separately is fully tensorial.
Sorry for the naive question.
No, that was a good question. In fact, what I should have said is that once you encode stuff in this guy, then these are just the things that I wrote down, and there is no local. It's just like whatever globally. Yeah, they're perfectly global. It's just I cannot simplify the. Like if you wish, the way you recover the usual setup is like I did it in a simplified way, but I kind of took the local freshness that it corresponds to this. But this is completely global. Thank you. That's a very good question. Okay, so there is two little things that I wanted to mention that I think are interesting, irrespective of what theory you're working with, and that's the issue of the field space. So this seems to be very underappreciated in the literature, but here it's kind of very interesting. And the question is essentially, okay. Informally phrased, this question is like, what the hell is this? Okay, so I mean, I use this variational notation of like infinitesimal thing, but like, what do you mean by that? As as physicist, or as physicists would say, like this means that you take the stuff, you deform it a little bit, and then you compare the two things. But now this rho, now this transformation that I brought to you, it deforms both metric and it deforms the metric in particular, and hence the thing delta should be different than two things. But if the two things now live different in bundles depend on the metric, then what does it actually mean to compare them if they live in different bundles? So what do I actually mean by these formulas? Or what do people mean when they do that? So what is delta epsilon, let's say rho? What's the meaning of that? And the meaning is kind of interesting, although not very talked about. And the fact is that the field space is really a vector bundle. So this is the field space of all fields, space of all fields, and it's fibered over the space of bosonic fields. So what I mean by that, here means the points down here are just parameterized by a choice of these two guys. They are infinite, and this is really data over manifolds. This is infinite dimensional now. So here I am with 50. But yeah, you just specify a point that gives you you specify a G and a sigma over the whole manifold that gives you a point in this space. And once you specify a point in this space, then you can define what these spinor bundles are, and then you can say that the fermions are simply elements of the fiber. This thing here is the set, if you want, of this. And this looks like a small thing, but actually it's a big thing in conceptually because the way people think about field theory is that take your fields, then you evaluate your fields at point on your spacetime, and then if the people treat these evaluated fields as coordinates on the field space. So fields provide you coordinates on the field space, but not these guys, because these guys do not give you anything. There is not even like any sort of open patch here. These things only make sense on the fiber. So they don't give you. You cannot take a partial derivative with respect to those guys in the same way that you do like elsewhere. And now the problem that I mentioned, the problem here that you have the supersymmetry. So supersymmetry now is epsilon. This is a vector field on this guy. That's what S0 face of field. So there is really some sort of arrow sticking in here. And the problem is that you want to compare on the supersymmetry, which in particular lets you change the geometry from one to another. So you want to now compare and calculating this spinor in two different fibers. So what do you do? You use connection if you have one. And indeed, there is a natural connection. There is a natural connection. It's very natural for the sake of time. I won't say what it is. You can figure it out. It's actually not difficult. If you think about infinitesimal parallel transport. And using that connection, now this guy, and this guy, these are this is the horizontal part of the symmetry vector field, and this is the vertical part of it. So that's the meaning of this, of these expressions. What you really have is a vector field on this big space, but the formulas you see, they correspond to the vertical and horizontal projections of that thing. And yeah, this is pretty interesting, at the very least for the fact that this connection that you have actually has a curvature. So if you would move in two different directions in this one-dimensional picture, difficult to imagine. Okay, if you move in two different directions, let's say you deform your metric in two different ways, there will be like two different tangent vectors. I'm ignoring the sigma for now. Then this thing should tell you a curvature is something that if you give me two vectors, then I produce to the endomorphism of the fiber. The fiber is where these guys live. So let's see what do I get if I act on something. Endomorphism I can draw. I find that this is 1/16 of the commutator of these two guys acting on. Sorry. Okay. Yeah. Okay. So there is a commutator, and then I take AB equation, and then you take Clifford action on rho. And there is a similar for psi. Important thing, there is a curvature. Okay.
This commutator.
It's the combinator of endomorphisms on its
Okay.
It twice.
Okay.
It actually whole of this, it holds every point on M separately. So we can, even though I talk about infinite dimensional stuff, we can actually, it comes from point-wise construction. So it's really a finite dimensional story. Okay. There is a similar thing that I wanted to. Yeah, okay, maybe I can say that. So there's a similar story how you can define a lead derivative of spinors, which would explain what these things are. Sorry, this guy, and this guy, and this one. Okay, let's say okay, if anyone's interested, I can tell them later. So this is a skippable part. Lead derivative of spinors, written in looking for papers. There you go. These spinors, again, natural interpretation which again uses the connection on the proof base. This is interesting, but let me omit that. Let me just state the theorem. It says that if you now take a section of the current algebroid, which is the thing that parameterizes the generalized diffeomorphisms. I didn't speak about that much, but if you take also supersymmetry, which, as I said, was an element of S minus intensity. Now, and this guy will give you a particular vector field on the field space, delta zeta, and this thing will give you a delta epsilon. That's the supersymmetry that we discussed. So there is two vector fields, and some details. We can now study the algebra of them. And you will see that if you take two different zetas, the thing that you get here will be the lead derivative. So this is simply said there is a group diffeomorphisms, or in our case, generalized diffeomorphisms, because it's current now, but feel free to ignore that subtly. So this is fine, this is what you would expect. There is a similar thing for diffeomorphism and supersymmetry. For those of you who know supersymmetry algebra, this thing just said that commutator of the translations is 0. In this case, okay. But okay, the most interesting part, it will happen when you have a combinator of two supersymmetries, let's say epsilon 1 and epsilon 2. And this is what the theorem actually says, or the theorem, because there is actually a rigorous proof that we have in the paper, although it's really hard, it's even much harder than the reasoning thing. And this is actually the core of the supergravity calculations. So this is very interesting. So if you act on some field, phi, where phi is any of your class of G, sigma, psi, rho, then what you get is you get a diffeomorphism parameterized by some zeta. Okay, this zeta is 1/4 minus 2. It's built out of these epsilons in some particular way. If you know supersymmetry algebra, you should recognize this. There is also, as appropriate to local supersymmetry, accompanying supersymmetry transformation, where the parameter is now minus 1/2 of zeta slash on rho. But most important, and this is what the whole story is about, there are terms proportional to the equations of motion of the field phi, and this all phi is 0 if you have Bernoulli fields, and for fermionic fields, it's not 0, but it is equal to something for this one slash. This thing slash plus 1/8. Epsilon 2. And this thing is rising with epsilon 1. And this is the theorem. If you study the dimensional vector fields of this space, then their algebra actually looks like this. So it's not really an algebra because this thing doesn't close, it only closes on a shell. And if you look at these expressions, or in particular these guys, then this precisely gives you the last two lines. This is the term which are quadratic antifields. And maybe the biggest theorem I should say is that this thing actually satisfies classical master equation, which we verified by hand. It also took us a little bit of time, as you can probably guess. But yeah, that's mostly what I want to talk about. If anyone is interested, I can talk about the directed spinners. And also, I can leave it as a question if anyone is interested as where we are actually going with this. Thank you.
So I identify your symmetry and the rest is like canonical construction.
Second, sir?
The rest is once you know what your symmetries are, the rest is canonical DB.
Well, yes, or well, morally, well, okay. So it's true that the hardest part of the classical master equation for this is this calculation.
Right.
It's true, but it's also not clear because in principle this there could be cubic, quartic, and higher terms.
Right.
And I think it was kind of quite an unfair fact to check that they are absent. So there is a lot of calculation beyond this. So it's not really it doesn't follow immediately, unfortunately. Also, there is some relatively beautiful but disturbing complications when you are calculating with this, because this is this leads on this is the cotangent bundle of some large space, and that large space has a connection. Yeah, this one. And hence, if you want to write down the Poisson brackets and you want to do it in terms of these variables, then they will not look that good, but there will be connection, there will be contributions coming from the curvature to this guy. And that accounts for that eats up some terms that otherwise would be present. And so it's natural, but it's a bit subtle to work with and kind of requires to develop the whole
So is it obvious what your gauge fixing fermion would be?
No, but
That's the hard part, right? For quantization.
for quantization.
For quantization.
But for quantization, wait, I thought if you do this Costello style stuff, then you don't need to do that. You can kind of avoid it by doing some logical. You did that?
You need.
Really?
Yeah.
Okay.
Okay. So what is your Lagrangian now? Over which you can integrate.
Right. But actually,
You need like decide what to throw out.
right. Well, not yet, because this is the classical
This
part.
class,
But
yes.
I agree. But I mean, this theory is like horrible if you want to quantize it. But I will take this as an incentive to say actually what the mathematical kind of conjecture behind all of this is. So there is a conjecture of Costello and Lee, which says that if you take this thing, which they didn't know, they just knew roughly how it looks like, but no one constructed it up to essentially now in this full generality. So what they say that you take this theory and you look at a locus where you have your bosonic field, which is this guy and this guy, but you also allow your E, which is the supersymmetry ghost, which normally you would be an odd beast, but here it's even because supersymmetry was an odd symmetry. So it's actually there is Z times Z2 grading in all this, and they kind of, if you sum them up, you get the Z2 grading, and this E is again an even variable. So if you study critical points of the action functional, where those things are non-zero, which is the same thing as to say that you study the points where the BB differential vanishes. And if you find a point where that thing vanishes, where this guy is non-zero, then you get and you perturbative index and you expand the theory around that point, and you get an L infinity algebra, and that should be the L infinity algebra that governs the Collier-Spencer theory, or the BCOP theory as they call it. So it should be kind of related to the deformation theory of complex structures. And that's a conjecture that if you expand it, I mean, of course, now we have it, we can just say that this is something plus perturbation, we can expand, but it's not as easy as that because there is some it's not easy. But the conjecture is that if you take this and you do what they call a supergravity, do a twist of supergravity by which I just mean this thing, look at the locus in the BB space where this thing is non-zero, and expand around that point, then the theory again should be much smaller in some sense and should correspond to in a cosmological sense, process, and each corresponds to BCOV theory, which is known. And they have a concrete expression for what the theory looks like, and they even BCOV. So they call it the BCOV for Versatile-Teokuri-Valach, which but other people call it the Kodaira-Spencer theory.
This is analogically complex variable. I mean, because complex variables, complex manifold has some known variation of formula coming from Kodaira.
Yeah. So
Spencer cohomology, I don't know if it can be corrected by, but it can be cohomology and variation are corrected for it.
right. So this non-zero spinner here, if you find a critical point of this, where this it's actually easy to kind of check what the conditions are. And the condition is that this is a pure spinner that follows because you want some vanish somewhere, I forgot. And it needs to be covalently closed, which means that it should give you a 10 dimensions on. It should give you a. For instance, Calabi-Yau 5 folds would be an example for such a point. Having the critical points of this.
Why this E important? Why you mentioned E?
So E is important because E is the covariantly the conditions for this thing being a critical point. This guy tells you that this thing has to be covariantly constant. So it's a covariantly constant spinner. With the normal geometry, that will tell you that the manifold is Calabi-Yau, let's say.
So it doesn't need that the manifold is without curvature. It's flat.
Well, in the particle Calabi-Yau field, this should be rigid flat, but I mean, this is a more general story, so that means some more general. Sorry?
Oh, okay.
But it also, I mean,
It is connected, but not the same. As flatness, it is some partial flatness.
okay,
Creating some E.
right. But it also, I mean, if you look at this in some other. Okay, yeah, yeah. But in any case, this is connected. Without it, it's just something. Okay, with this thing, with this thing around, you kind of enter the realm of complex
I
geometry.
know this Spencer theory of movies, right? Simplifications on one side and problems on the other side, which make that solving or not solving.
But maybe just one thing to what Brian was saying is that like Costello and Lee showed that this thing that they call BCOV theory, so it's a reformulation of the Kodaira-Spencer theory. They showed that admits a deformation. Sorry, they showed that that admits a perturbative quantization in clear sense. So they proved that all the obstacles vanish, even though it's non-normalizable.
Yeah.
It can be quantized consistently.
Yeah.
Pretty cool.
There's one question from the online audience. Eugenia is asking, quote, does the commutator of the infinitesimal transformations in the direction of the sections of E close on the current logical break? Unquote.
Right. So that's right. So I think she means this one. Yes. So this yeah. So the only place which doesn't close on shell is the commutator of the supersymmetry. All the other diffeomorphisms with diffeomorphisms with SUSY, they all close off shell. And in the case of diffeomorphisms, it's even these things even correspond to a Lie algebra.
Commutator.
The commutator, yeah.
And is it a supercommutator or a commutator? This is
Well, all these things to get. No. This is the commutator because even though this is like odd parameter. Sorry, this guy is odd, but the delta of that is even. So so these transformations. That's a very good point. These transformations, even though they include some odd parameters, they don't change the parity of the original thing. So this was even, but because this is odd and this is odd, this is again even. So these deltas are really even vector fields on the field space. That's why I only write commutators. So yeah, did I answer Eugenia's question?
She might be typing something.
And anti-commutators need an evaluation. Anti-commutators will be different. So if you have plus, minus, they can be different.
Right. I mean, anti-commutators are written in here somewhere, but the way I wrote it is that this uses only commutator, but yeah, it's kind of equivalent to
Also, there is a follow-up question. Have you thought if the supersymmetry algebra could be seen as some super algebra, it would be
Okay, that's okay. I saw the question. So yeah, so my question is asking whether you can kind of encode the supersymmetry by saying that the Courant algebra is not just P plus T star, but Lie algebra, which is kind of the transitive case that was behind this, which is the one that gives you diffeomorphisms, B field and H field gives transformations, which is this is together where this zeta lives. Other thing is asking if you can add it is a parameter. If you can add kind of spinner, maybe some odd sand, then you can encode the whole algebra in terms of some supercomputer. I don't know. I know that people have thought about this for a long time, and many people, and I don't know if there has been any success in. I don't remember what the problem with that is, but there should be some problem because people say that there is, but it doesn't work. At least it doesn't work as one.
But with some graded manifold, right? With
Yeah.
homological, you have the cube for the SBV, so which squares to 0.
Right.
So you can make up a graded manifold with
Yes, but okay.
homological vector field or some structure. Or
But it doesn't give you like a finite dimensional.
no.
So yeah, I mean, maybe one problem is that because these guys don't, the bracket on these guys doesn't close.
So it is from L infinity algebra.
Yes, but a big one.
A big one.
Yeah, but yeah, good point.
I have a question. I think that the Lorentz group with signature 9 and 1 is closely related to the obtenants. So is this
Yeah, right.
can this be somehow relevant for
Yes, and yes, but I don't know about I mean, it is so there is so the reason why these calculations are so hard is that the group behind them is kind of large, and I prepared this counting that I did like in the kind of physically relevant case, the degrees of freedom of this basic theory is like 13,173 degrees of freedom. It's a meaningless number to say that it's complicated. But yeah, what makes it partly complicated is that there is this kind of Clifford's. There is lots of kind of identities that are behind this, and the reason why it took us so long to kind of show the invariance of this under this very concrete transformation, which sounds like a very straightforward task. The problem is that there's a big ambiguity in writing these things because of the so-called Fridrich identities, and there's lots of algebra around, and part of one way to kind of gain some insight in that algebra is to use the octonion, as far as I remember. So it might be useful for like I don't know if you can use them directly kind of simplifying this. I mean, this is already kind of I would say this is already very as simple as it gets. But yeah, there is no concrete role of the octonion here. But at least in these proofs of which things vanish, etc., that might be useful, and some of the statements might be easily derived in that way. But we did this kind of first. But yeah, in some sense it enters. And Martin Sederwall probably knows more about this. I mean, he definitely knows more about this.
So it has some numerology, mystical behind its coefficients.
Yeah. This thing is just 3. This is just 3 times 6. It's 3 times power 2. The same for this one. Which is a great improvement. If you look at the old papers, they have things like 7/15 and stuff like this.
But this is very good described in the free lectures.
Okay.
I think this spans of 16 dimensions set.
Right. Yeah,
Sections.
I mean, the fact that I take it as a huge success that we managed to write in a way that there is one here.
Yeah.
That's very non-trivial. And the rest of it is kind of, like there is this anti-symmetrization 3 indices here, which kind of really means that the way you should look at, you should include 1 over 3 factorial in there, which should always lower the thing by 6, and then it's just some power of 2, which is related to the dimension of the spinor representation, which is 2 to some power.
Okay, so
it should be that, but I don't. I don't have a kind of sneaky way to kind of get rid of that at all.
Can you add something about it further? Can you make it longer?
Very good question. Yeah, so one important thing is about the supergravity. That's very good. So this n equal 1, b equal 10 theory is fully specified, at least locally. There's some global things you can do with principal functions. The only thing you need to choose locally is you need to specify a Lie algebra with an invariant pairing. Once you fix that, then the whole theory is fixed, and symmetries of it are fixed, and there's no more. It's like it's unique. So and then there should be no way to. I don't think there's a rigorous claim to this, but at least really that there is no way to get this. Any deformation, I think any deformation that you would do would just amount to in some way modifying the Lie algebra. And there is another story which is called type 2. That one is unique completely. Like there is no freedom there at all. So that's kind of our one over to the next goal. So yeah, these things are very.
So normally you start with some gravity, this R, yeah. Then you add some Dirac term for spinors. Then
Yes.
you add some.
And there is a unique.
Dirac for densities, it already doesn't make sense because we don't know what's the.
Oh, I didn't say that, but yeah, there is.
It's normal. It's normal. It's something like that.
Well, I kind of try to skip over that. So there is general geometry, there is natural way for these things to act on spinor Hall densities. So Hall density there is kind of important. For
some
some.
don't remember it. Then you add Dirac for spinor.
Yeah.
For gravity, no, times some
So the claim is that
vector correction.
so the claim is that once you fix this first term or maybe first three term or first line or something, then the rest should somehow follow in some way. That there is like a unique way to extend this. And even the way people start this, they look at this n equal 1 10-dimensional superalgebra, which is just some concrete super algebra. You look at the lowest erect of that. That's the thing that tells you that you have G, B, A, Y, and the other two guys.
And you end up with something adjoint representations, or you take even tensor products of adjoint with something.
I think this is just the only error, the smallest error of the n equal 1 equal 10 super algebra. There is
Smallest scalar, I can imagine that I take representations which are sub-representations of 10-folded, 12-folded tensor products, and I project on scalars. They should exist because you take spinors which are in available in SO in general, not only projected but available, but there should be some scars which may be worse. So one scar than this actually scalar for the representation.
But I mean representation of the super algebra or of the Lie algebra? Of the Lie algebra. I don't know. So you need the super Lie algebra. So the smallest error tells you what the fields are, and the claim is that there's a unique way to do an action for them. And it looks like this, and the extension looks like this. And that claim is kind of a claim, but it's believed by me. Yeah, I think probably I'm taking everyone. So I'm happy to answer more questions, but maybe let's close the seminar. Thank you for your attention.